All right, let's get started. Is my screen visible?
Yeah, yes, sir.
Okay. All right. So how was quiz one? Level of questions, difficulty, and length, and all that. Was it all right?
Yes, sir.
Are there any queries?
So it was good.
Any doubts regarding any of the questions?
Sir, first question.
No, there is a doubt. Is it just one moment? What question do you have doubt in? Could you let me know because I don't remember the questions.
Yeah, the one with Venn diagram.
Just one. What pages?
So that's that theory. Thank
You have to tell me the whole question. I don't have it in front of me right now.
Okay, give me a second.
Okay, maybe we'll take it at the end then. Let's get on with the summary, and then at the end we'll take up doubts from quiz as well,
Okay, sir.
in addition to everything else, in addition to doubts from week 5. So in week 5 you have the two main concepts are one-to-one functions as well as composite, and related to one-to-one functions is the concept of an inverse. We'll go through all of them one by one. So you have already seen what a function is way back in week 1 itself. One thing was that a function is a way to map elements from one set to another. The, the diagram that we had was something like this, where we would say each element over here has some image over here. What was not allowed was things of this form. This was not allowed, right? So this is your domain. This is your codomain. Elements of the domain, which is denoted by A over here, are mapped to elements of the codomain. But each element of A should be associated with only one. There should be only one corresponding B. And there should be one corresponding B. There should not be any elements of A without any images and so on. So this is not a function, but if I remove this, this is a function. So it can happen that elements of B are not images of any point. That is okay. And it can happen that one element of B is the image of two different elements of A. That is also okay. But what is not okay is if an element of A does not have an image, or if it has multiple images. Every element of A should have a unique element in B. A and B we will be calling the domain and the codomain. And this sort of diagram is okay to keep as a prototype whenever you want to think about certain properties. But usually we will be describing functions just as a function from A to B, and we'll give some formula for this, some expression in terms of x. So the the point is that if I know x, I can compute what f of x is using the formula specified. So if you want specific examples, you can take mod x, for example. Now, and A and B are, let's say, R and R. This is fine. So even though not all elements of the codomain are images, so what elements of the codomain are not images under this function?
Below 0.
Yeah, negative numbers are not going to be images because the modulus function is always positive, non-negative. So for 0 it is 0, and for every other for non-zero numbers it is strictly positive. So you can never have this to be negative, the function value to be negative. And as it is, this is not a surjective function, if you remember, surjective or onto. But if you have something like this is okay. Now it's not a function because yeah, I want 0 to be included also. So if I have 0 to be included and I have only the set of non-negative numbers as the codomain, then every element of the codomain is also image of something. Okay, so this goes back to injectivity, surjectivity. Now, injectivity I have not talked about. Is this function injective or one-to-one?
No, sir.
So can you give me a couple of elements which are mapped to the same thing?
1 and
Same.
-1 or 2 and
Yeah. So
-1.
f of 1 is equal to f of -1, and 1 and -1 are distinct elements in the domain. So this is not a one-to-one function. So yeah, the recap does contain that also. So I'll comment on that after I get to that point. The first point is clear, I suppose. What is a function? What is the domain? What is the codomain? And x is mapped to f of x. This is how we will be writing it. And for this session, as well as for most of the course, we'll be considering functions which are defined on some subsets of the real line, and their images are also in the real line, which is R, the set of real numbers. If you don't want to think of it as the real line, you can just think of it as the set of all real numbers. Now, in such a case, what we can do is we can draw the graph of the function. Remember that a function was also defined as a special case of a relation. So what was a relation? A
It was
relation
the
from A to B,
subset
let's
of
say.
the Cartesian.
Yeah, so a relation is just subset of relation on A, relation from A to B is a subset of A cross B. Now, when I have a function, if I collect, suppose I have this function f from A to B, I can collect all the pairs of the form x comma f of x, right? I let x be arbitrary element of the domain, and I pair it with its function value on the codomain. So this is a subset of A cross B. Now, this is called the graph of the function. Why is it called the graph of the function? Let's add a page just one. So now let's take a simple example. F of x is equal to x squared. Now, what are the points which are there in the graph of this function? I'll write it as gamma of f. So these are all the points of the form x comma x square, right? X in R. So where are these points? These points are in R2. So I can look at the Cartesian plane and corresponding to every x.
Integer, na? X is positive integer.
No, it's not necessary to be positive or an integer. The domain is R itself.
Okay. Means it can be negative also.
It can be negative also. So suppose I take the value of x to be equal to 1. What is the corresponding value of f of x? That is also equal to 1. So I'll have this point to be in the graph. Right, so I'm collecting all the points which are of the form x comma x square. So for example, for the value x is equal to 0, I'll get the origin itself. Let me not denote this by that. So let's just say this is at 1, this is at 2. So at 2, what happens? What is the value of the function?
4.
It's equal to 4. So 1, 2, 3, 4, somewhere over here. But what happens on the other side? What happens at -1?
That also.
So that will also be 1. And then again at -2, you'll have 4. So what you will get if you now I've picked a few points like -2, -1, 0, 1, and 2. If you collect all the points, all the continuous points, and you look at the behavior, or if you use a graphing software, it is easier. You'll see that the graph of the function will be like this. So what is this? This is precisely the set of all points of the form x comma x square. If you collect everything, this is the line that you'll get. Maybe we'll use a different color for it. Okay, so this is the graph. Just make sure that all the points are there. All right, so roughly the graph of f of x is equal to x square looks like this. So this is also written as y is equal to x square. Okay, so coming back to that. The graph of a function from a subset of R to a subset of R can be visualized in the Cartesian plane R2. And how do you do it? You just collect all the points of the form x comma f of x. You vary x in the domain. Look at and at the x coordinate equal to x, you put the height equal to f of x. Then you will get a collection of points, and that is called the graph of the function. Now, yeah, one-to-one function, this definition also we have seen. Instead of using this visual representation of one-to-one function, what we do is we give an algebraic condition sort of. So distinct pair of elements need to go to distinct pair of codomain elements. So that is what one-to-one means. Something like exponent. So something like this should not happen. So here you see 1 is not equal to -1, but, or let me write it above itself. 1 is not equal to -1, and f of 1 is equal to f of -1. Such a thing is not permitted for a one-to-one function. Yeah, are there any doubts?
No, sir.
Okay, if you don't have any doubts, please mute yourself. All right, so why were we talking about the graph of the function is that, so as soon as a relation is given, you can also plot the points. So if you have a relation, so there was nothing specific about this being a function. A function is a special kind of a relation, but as soon as you have a relation, you can plot the set of points, right? So what is a relation? As we said earlier, it is a subset of A cross B, but A and B we are assuming to be subsets of the real plane, real line. So the relation itself sits as a subset of R cross R. So you can draw the graph of a relation. You don't really need a function. So now how does drawing the graph help? Like what information can you derive from the graph of a function? So there are two tests. One is called the vertical line test and one is called the horizontal line test for obvious reasons. Vertical line test is where you draw lines of the form x is equal to x naught and you see if it intersects the graph of the relation in two or more points. If such a thing happens, then the relation is not a function. And the horizontal line test says that if you have a horizontal line which intersects the graph in two or more distinct points, then the function is not one-to-one. Let us see this in specific examples. Let's try to draw the graph of all these functions and see what the horizontal and vertical test means in each of the cases. Right. So what is the graph of y is equal to x square? We have already seen that, right?
Drawn and
Yeah, we have just drawn it.
parabola.
So for this case, so it's something like this. It's not passing through the origin, so I'll not approximate it. So it's something like this. Now, wherever you draw a vertical line, something of this sort, is it going to intersect this graph in more than 2 points? Is it possible that it is going to intersect the graph in more than two or more points?
No.
No. But what about horizontal lines?
Is intersect.
Intersect at 2 points. So every horizontal line other than the one at 0, and okay, below 0, if you have horizontal lines, they don't intersect the graph at all. But for positive values of y naught, y is equal to y naught, if you draw the line y is equal to y naught, it is going to intersect the graph in two distinct points. So in this case, vertical test confirms that this is a graph of a function, and that function is, of course, f of x is equal to x square. Horizontal test implies that f is not one-to-one. So why does the vertical and horizontal test even work? So if I have some graph for which a vertical line intersects it in 2 points, what does that mean? So let me draw something which I'll erase a bit later. So you suppose you have something like this. Now you draw a vertical line and it intersects it in 2 points. So what does this mean?
For single value of x, there are two value of y.
Yeah, so there's like x comma y1 and x comma y2 both belong to the relation corresponding to this graph. But when does a relation become a function? A relation is a function only when given a value of x, there is a unique y such that x comma y is in R. So an x should be associated to a unique y. So such a thing cannot happen. So this is not a function. So this is why the vertical test confirms whether or not the given graph is the graph of a function or not. And what about the other one? What about the horizontal line test? Now, in this case, you have seen that the vertical line intersects the graph in 2 points. So what do those 2 points look like? What is common for the 2 points of intersection?
Y is common.
The y coordinate is common. So no, x is not common. The height is common. So it is intersecting at a particular height, right? So this is suppose this line is equal. So horizontal lines are of the form y is equal to y naught, isn't it?
Yes, sir.
Yes, sir.
So any point on that line, in particular these 2 points. So suppose this is some x1, or yeah, let's let it be x1 y naught, because this is on the other side. I'll just call this one x1 y naught, and this is x2 y naught. So what does this mean? This means that there are two distinct values of x, x1 and x2, which are mapped to the same y. So this is why the horizontal test is used for injectivity. So once again, to summarize, vertical test is when you draw lines perpendicular to the x-axis or vertical lines or parallel to y-axis. All of these things are the same. And even if there is one line which intersects the graph in more than one point, then the given graph is not that of a function. Now, suppose you have a function, then you can do the horizontal line test. And even over here, even if there is one horizontal line which intersects the graph in more than one point, then the function is not one-to-one. Is that clear?
Yes, sir.
Yes.
Well, let's draw the rest of the things and see what the tests reveal. So points of the form x comma y. So here it will be y square comma y, right? So the second one is all the points of the form y square comma y. So what would the graph look like?
Parabola view, right side.
Yeah, so it's going to be a parabola which looks something like this. Something like this. Okay. Now, what does the horizontal and vertical test say? Or vertical first?
It is not
What happens when
perfect.
it?
So vertical
It's the 2 points.
point is
Yeah, so
intersecting two, so that's why it's not a function.
yeah, so it's not a function of x, right? So this is not the graph of a function in the variable x. So then horizontal test doesn't make sense. But even if you do so, horizontal test will pass because there is no horizontal line where there are two or more intersections. But this is not a function itself, so talking about one-to-one or not doesn't make sense for this. And what about y is equal to minus x? What is the geometric description of this line? Okay, well, what is the geometric description of this relation?
Having negative slope.
Could you repeat?
It is having the negative slope.
It's slope minus
Linear,
1.
linear only
So
negative.
so it'll be
Yes, sir.
something like this. So this is the graph of y is equal to minus x. What about the vertical and horizontal test for this?
Both will pass.
Sorry to the
Excuse me, sir. Sir, what can be the set of values for this y equals to minus x?
Yeah, that's a good question. So here we do have to say, so as subsets of R cross R, meaning you take the values of x from real line, whichever, so you collect all pairs of the form x comma minus x as x varies in R. So this is the infinite straight line. Here I've drawn a part of. Okay, so here the vertical line, is there any vertical line which intersects the graph in more than one point?
Sir.
No, so this is a function.
yes, sir.
And the function is actually just f of x is equal to minus x. So in this case, if you try to write it as a function, you see you'll run into a problem. So if you want to reformulate y square equal to x as y is equal to something, so there do you see the problem? What happens if I try to write y in terms of x? for the second example.
minus that root factor.
It's not reversible.
So you'll get plus minus. So here x is positive, first of all. But you'll get plus minus. So there is not a unique value of y associated to any given positive x. So that's the problem. So you can't
But
write it
if,
as a well-defined
but if
function.
we say we consider this x is equal to y square, can it be termed as a function if we take y-axis as x-axis and x-axis as y-axis?
Yeah. It's so x can be written as a function of y. So that would give you just this one, the first thing itself. So, but the vertical line test is for writing y as a function of x.
Okay.
So if you're writing x as a function of y, then then your axis will also change. So your check for a function will become a horizontal.
Yeah,
So we can
that's what I
redefine the
mean.
function.
That's what I mean in the second equation that you're writing. So can we view it in terms of y, like it is a function around x-axis?
You can write this. This is the graph of a function of y. That is okay. But here you usually define what the domain and codomain are, right? So here we have defined the elements of the domain as x, and we define the elements of the codomain as y.
Y
So
belongs
that
to
is
orthogonal and range is 0 to plus infinity.
if you write it as that, if you flip the variables and define this as the domain and that as the codomain, then yes, this will be a function which has domain as R and codomain as positive. It will be the same as this. It will be the same as the first one.
Got it. Thank you.
But that's not what we are considering. So here we are only worried about writing y as a function of x. Right. So for the third one, vertical test says it's a function. And what about horizontal test?
It is to taste someone.
It's a 1-1 function,
Yes.
right? And the last one, what is the graph of the last relation?
The straight line from 0 to positive infinity.
Well, straight line from 0 to positive infinity is not a perfect description, right?
I think
How do you
that
describe a line?
V-shaped graph.
A very positive x-axis.
So, like if we take the negative values, then also we get the positive in the model. So I think that V-shape will
Okay, let's jot down the possible answers. A V-shaped graph. Any other guesses?
Straight line from in first quadrant with 45-degree angles.
Okay, straight line. Is it just in the first quadrant, or
Oh,
will it go other way also?
I think output will be positive always.
Positive x and
Don't know.
positive y.
See, x and y could be anything. Why do they need to be positive?
The axis itself, I guess.
Is straight line with the slope of from 0 to infinity in a first quadrant.
Slope what? So you're saying it is just this.
Yeah.
Yes.
Right, so this is B, or maybe it is a V-shaped thing like this. So that would be A. A is the whole thing. B is just that part. I'll put A over here, let's say. But yeah, both are incorrect, but there are partial ideas there. So first of all, let's see. Is 1, 1 a point on the graph?
Yes.
Okay, is 1 comma minus 1 a point on the graph?
Yes.
Yes, right? Because
No.
mod of x is equal to mod of y is satisfied.
Yeah. Got it.
Yes.
Right? Now, is minus 1 comma 1 a point on the graph?
Yeah. Yes.
Yes. And what about
Yes.
minus 1 minus 1? That also
Mm.
satisfies
Yes.
mod y is equal to mod x. In all cases, mod y and mod x are both equal to 1. So at least this point, this point, this point, and this point are there. Now, can you
So
improve your
X type
guess?
graph will be there. X type. Like upward V and then upward. I think.
So, well, that is the correct answer. But a better description of the thing is it is a union of two straight lines. One with slope plus 1, one with slope minus 1, both of which pass through the origin. So this is also something that you can be a bit more careful about. Like even when you know the answer, how do you explain it precisely? That is something that will be important. Okay, so this is the graph of the function. The graph, it's not a function. So is it clear why it's not a function?
Yeah.
Yes.
Here, everywhere the vertical test fails, except at the origin, at x equal to 0. And it is also not 1, 1 in nature because horizontal test also fails. So to understand what it means to draw the graph of a relation, please focus on this. And if you have already understood it, it's fine. If not, then spend a bit more time and see how we concluded that the graph of mod y is equal to mod x is actually the union of two lines passing through the origin, one with slope 1 and one with slope minus 1. Okay, so
Sir,
this
can
is
you
about
show how to solve this two mod together?
which
I
one?
didn't get that. The
So
equation,
you didn't understand why the graph of this will be equal to that, equal to the one we have drawn. Is that the
because
thing?
I don't know how to solve the two mod together.
Okay, so what does it mean to say mod y is equal to mod x? So if I have a point which is this, and I'm told that mod y is equal to mod x, what does this mean? What are the possibilities?
X can be taken as positive, then Y positive.
So I would say that this has two cases. It's either x is equal to y or x is equal to minus y. Whatever x and whatever y may be, if I want the absolute value of x to match with the absolute value of y, what are the two cases? So suppose I'm looking at y is equal to 2. I want mod x equal to mod y, which is actually mod 2, which is 2. What are the set of points which have mod x equal to 2? X is equal
2
to
and
plus 2 and
minus
x is
2.
equal to minus 2, right?
Yeah.
So given any particular y, value of y, let's say you take y is equal to y naught. Here I've taken y is equal to 2. Now y is equal to 2 is just any arbitrary point. You could have taken any y value. If you fix the value of y, then the values of x corresponding to that are plus y and minus y, right?
Yes, sir.
Right. And where do those lie? So if I have x is equal to y, what is this geometrically? What does x equal to y describe?
For every value we take,
No,
it
just
would
if you're
be
given
like
the equation y is equal to x, how would you describe?
Either y is plus x or minus x.
No, y is equal to mx plus c. Y is equal to 1x plus 0. What is this? This is the equation of
Line.
line,
a
straight
line
line,
with slope 1 with
straight
y-intercept
line.
equal to 0. So you
Yes.
get this part. So this is x is
So
equal
that
to y,
first quadrant.
or not necessarily in the first quadrant. So y could be negative, y could be positive. I don't care. So as long as x is equal to y, I'm good. I could even have -2, -2. That's okay for me.
That
Or -2, 2. Here it is x is equal to y, so we'll take 2 comma 2, or in this case it is 2 comma 2, but you could have, if you as you vary y,
so
x will also vary, but
also in
in
the
such a way
third
that x is
quadrant
equal.
and first quadrant it will be same.
Yeah, first quadrant and third quadrant. So that is one line, or x is equal to minus y. What is x is equal to minus y? Or y is equal to minus x? That is yet another line of slope -1 and y-intercept equal to 0.
So that opposite.
So or means you have to take the union of the two sets, right? So what does A union B mean? X is in A, or X is, let's not talk about X, that might be confusing. Let me take an element P. A P element P belongs to A union B, means P is in A or P is in B. So whenever you have or, you have to take the union of those two sets. So this is a straight line with some description. This is a straight line with some description. You have to take the union of these two straight lines. And what you will get is this diagram. Okay, now I'll move on. Maybe if we have time at the end, we'll come back to this if there is still confusion about this.
Okay, sir.
Right? So yeah, some tests for one-to-one function without even having to go to anything else, even without well, this is a corollary or consequence of the horizontal test. If you have a strictly monotone function, monotone means it is either increasing or decreasing. So here, the condition that is written over here, this is for only for increasing. So for decreasing, you will have x less than y implies fx greater than fy. So for strictly increasing function, first we'll focus on. Then the function is one-to-one. Can someone give an argument for this statement using the horizontal line test?
Y is equal to x square, that function.
No. I'm not asking for an example. I'm asking why is this statement true in general for functions, for increasing functions? So what is an increasing function? An increasing function means you will never have things like this, right? So here it is decreasing. So such a thing will never happen. So you'll have something like this. Maybe at parts it will be slow, maybe at parts it will be fast. But overall, it'll keep increasing only. So when you have such a function, is it possible that a horizontal line intersects it 2 times?
No.
No,
No,
sir.
sir.
Because as soon as you have something like a 2 times intersection, you look at the corresponding values of x and y. So here x is less than y, but f of x is equal to f of y. And that is not going to happen because this is a strictly increasing function.
Sir, what if the function is constant at for some time in between?
Here you want it to be strictly increasing, right? Strictly increasing meaning it will never be stable even for a bit. So that way you can take even the constant function y just for some time. You could take an identically constant function that will trivially fail the horizontal line test. But
Okay.
even if you have something like this and then this, over here also you have distinct values of x mapping to the same value of y, right? If it stays constant for some time, unless it is something like f of x is equal to x square, which does not really stay there. All right. So if you have an increasing function, strictly increasing or strictly decreasing function, then it is automatically one-to-one. So why are we focusing so much on one-to-one is the second remark, where towards the end of the session, we'll make it formal what it means to be reversible. But here I'll give you an idea. So once again, for the first level of understanding, let's take this sort of diagram where you have like finite elements mapped to another finite element set. Now, if I have something like this is a function, right? So suppose, say from A to B, this is a function which is f. Can I define a function from B to A such that it reverses the effects of f? What do I mean by reverses the effects of f? It will whatever f has done, it will undo. So it will take some image of f back to its pre-image. So if I'm going this way, using G, I'll be coming back this way, meaning this element B will be mapped to this A, or let's call f of A will be mapped to A.
But sir, that will be not be the function, right? Because one element of B is mapping two elements in A.
Yes, so that's the problem. So if you don't have injectivity, meaning if you have a case where multiple distinct elements are mapping to the same element, I cannot define the G of this function, G of this element. What is G of B? There are two choices. That is not well defined. That cannot be done. But the statement over there, the second statement, if you see, it says that if a function is one-to-one, then the function is reversible, which let's see. It doesn't say anything about the surjectivity. So let me just take like 3 elements over here and 4 elements over here. So if I map this to this, this to this, and this to this, and I call this as f2 from again some a to some b. Now can I define a function from b to a?
Does every
Which is
element
the
has
reverse
to
Yes.
have a image?
For a function that needs to happen, right?
Yes. So no.
But there is
So
an error.
I cannot define the reverse from B to A, but is there a way that I can define the reverse? It's actually called the inverse.
By removing the extra point?
Yeah, so what would be the domain of the inverse?
It will be the domain of the A.
No. If, the domain of the inverse will be something over here, right?
Yes, so that B part.
Yeah.
State of B, sir.
It can't be B because there are some elements which don't have pre-images. So there is a specific name for it, a name that you already know.
Range.
Yeah, so you have to consider the range. So let me write it as inverse now. Inverse of f2 can be defined f2. It can be defined on range of f2. Remember that range is the set of all points in the codomain which are images of something. So what happens when I focus on range is that I remove all the elements which do not have pre-images, and I'm assuming that the function that I start out with is one-to-one, which means that they don't have multiple pre-images. So what happens is that I have a well-defined way of going back. Is this clear?
Yes, sir.
Yes.
So this is why we are focusing on one-to-one now, because we want to make rigorous the notion of what is an inverse. So let's keep that aside for now and focus on a particular function which is injective, and that is the exponential function. So in this section, there are certain things which you have to just take as a fact. We cannot go into the rigorous proof of that, one of which is how to define the exponent of an irrational number. Now, what does exponent mean? So first of all, positive, we start out with a positive real number a. If it is convenient for you, you can take a particular example like 2 or 3 or whatever. What does it mean to say a to the 1? That is just a. Now, what
Yes.
is a square?
A into A.
Exponent of A is 1, exponent of A is 2.
Multiplied.
So, in general, you know for a positive integer what it means, right? It's like m-fold multiplication. At the same time, you know what it is for 0. You know what it is for.
One is 1 by.
So as a continuation, I can do this same thing.
A
No?
to the
I can just do this. So we know what it means to say a to the m when m is an integer. Now, what about things of the form, let's say a to the half? So this is why you'll need the positive real number part. What is a to the 1 by 2?
Root of
It is the root of a. So there is a real number such that its square is equal to a, right? So if you want to look at it with the graph, if I look at this thing, and if I look at the height y is equal to a, what is this point over here? It is equal to some x comma a, right?
Yes, sir.
This is the graph of y is equal to x square. But since it is on the graph, what is the properties? What is the equation satisfied by that point? Y is equal to x square, so it should be a is equal to x square. So there is a real number which when squared does give you a as the answer. Now the convention is to take the positive value. So that is what we'll do. Similarly, you can make sense of what is a to the 1 by n. Is that okay? Irrespective of what n is, as long as it is positive, there is a real number which when multiplied n times gives you a as the answer. So that is called a to the 1 by n. This much is known. If you know this much, then you can make sense of what it means to say a to the m by n or a to the power of any rational number is okay. Is that fine? You would simply do a to the 1 by n m many times, and that is how you would compute a to the m by n. Is that fine? Now, what about an irrational number? Give me your favorite irrational number, something like root 2 is something like 1.4142 or something like that. So how do I make sense of what is a to the root 2? What does this even mean? A to the power of a rational number, we understand. We know what it means. But what is a to the root 2? So to define this, what we do is we look at the decimal expansion of root 2.
I think that
Right? So
sequence is needed.
yeah. So you have to take a sequence. The theory of sequences is not something that you are familiar with already, at least most of you. So I'll just say this, and the proper argument for it will come maybe sometime later, even in math 2 maybe. But for now, just think of it like this. So what is the nature of the decimal expansion of an irrational number?
Uh,
So if you are given a decimal expansion of a number, how do you determine whether it is rational or irrational?
On terminating.
Could you repeat that?
Terminating decimal.
If it's not, it is terminating or not.
If it's not
repeating, sir.
terminating, then it should be that.
So
So
if
if
we
it is
have a decimal
terminating,
number,
it's a rational number.
so if we say if we have a decimal number, so if say 1.4, we can define it. So similarly, we
Yes.
can define it 1.41. Similarly, we can define it
Yes.
4.1 and then on. So we can define the whole
Yeah.
series.
Yes. So this is how you actually go about doing it. And irrational numbers have non-terminating, non-repeating. So a rational number could have repeating stuff as well, right? So there can be blocks which keep repeating themselves. But an irrational number will have an infinite decimal expansion. So there needs to be care taken to say that this actually approaches something. So what we will do is, if you want to calculate a by root 2, we'll do a, the one which is just a, and then you can go a to the 1.4,
Yes, sir.
a to the 1.41. All of these things are terminating, so they are rational numbers. You know how to deal with rational numbers. So we keep increasing 1
0.414.
more, 1.4142, and so on. So this is an infinite series of real numbers, and there is a notion of convergence of a sequence of
Convergence of sequence.
real.
Yes, sir.
So this actually happens to converge to some real number, and that is what we will end up calling a to the root 2. So if you actually take some particular value of a and start computing these numbers, you will see that it approaches some value, some real number. And that real number is what is called the exponent of a to the root 2. In general, if I'm given any positive real number a and any x, I can make sense of what is a to the x. This can be done. So a to the x can be defined for any a greater than 0 and x in R. Which means to say that I can define a function, fix an a, define a function whose value corresponding to the real number x is just a to the x. This is well defined as what we have argued so far without giving the proper proof, but we have said that there exists such a real number which is the limit of some sequence and so on. And that is the definition of the function. So we exclude this a is equal to 1 because in the case of a is equal to 1, what happens? What is the nature of the function if a is equal to 1?
1, sir.
So it is identically 1, right? It is going to be 1 to the x, and 1 to the x is always 1. So this is a constant function. It is still a function, but it will not enjoy some of the properties that we'll state later. So we'll just exclude it from our discussion. And this is called the exponential function with base a. Is this clear?
Sir, why the condition a is bigger than 0?
So if you have something like -1 to the root 2, you don't have a square root of negative numbers. So this thing is not guaranteed, right? So we'll go into complex numbers. So we are not doing that.
Okay, got it.
Square root of a negative number does not exist. So but as long as we stay within positive numbers, that is always guaranteed. You will always have nth roots of any positive. So yeah, that's exponential function. Now, well, properties of the graph. So I hope you have seen the graphs of this already. I'll just draw a rough sort of sketch. If not, just open any graphing software and plot it if you want to see it. If you want to see the correct graph, precise graph. Now for a between 0 and 1, let's just take some example, half. What happens if I take x to be very large positive number? So first of all, a to the x is this. A is equal to half. F of x is equal to half to the x, but that is the same as 1 by 2 to the x. Okay, maybe here there are some properties that you just take a look at. It is very natural properties. A to the r, a to the s is a to the r plus s, and a to the r to the s is a to the rs. All these things are enjoyed when you even extend it to real numbers. Also, all these things are valid. So here it becomes 1 by 2 to the x. So as I increase the value of x, as x gets larger and larger, what happens to the value of f of x?
It decreases.
It gets smaller and smaller.
Smaller and smaller. Does it go like this, smaller and smaller, or what?
No, it tends to 0.
It tends to 0. It always stays above 0, right? It's half to the power of something. So first of all, let's see what its value is at x is equal to 0. At x equal to 0, what is the value?
1.
This is 0, 1, because 1 by 2 to the 0, which is 1 by 1, which is 1. And then on, if I increase the value of x, then the denominator value increases. So you see this 2 to the x is an increasing function. Well, that will matter over here also. If you do this, then you'll get this for free. If you do the first case, you'll get the second case for free. So as I increase the value of x, the value of 2 to the x also increases. But since it is in the denominator, this will go to 0. It will never cut 0. Can it happen that 1 by 2 to the x is equal to 0?
No.
No,
No.
right? Then you will get some 1 equal to 0 kind of contradiction. So it will have such a behavior. And on the other side, also it is decreasing itself. So if you plot it, you will get a graph like this. Okay, so from this, all of the properties that are listed are clear, right? Range is 0 to infinity. Now, okay, on the other side, what happens? So if I decrease the value of 0, if I go more and more negative, what happens?
It's increasing, sir.
Yeah, so as I approach minus infinity, the value of f of x shoots up. Is that clear? Because half to the x, I can also write it as 2 to the minus x, right? So when I have a large negative value of for x, I'll have 2 to the power of something very large. And 2 to the power of something very large is very large, right? So all of these things should be clear from what we have discussed so far. Y is the range equal to positive real numbers. It is never equal to 0. The y-intercept is 0, 1. The x-intercept does not exist. It is also a strictly decreasing function. And what about a greater than 1? So instead of half to the x, we'll take 2 to the x. For this. In this case, the picture sort of inverts. What happens when I take a large value of x, large positive value, when I take for 2 to the x? First of all, we'll again note that this is 0, 1 is still there. And let's say at 1, what happens? It is 2. But at 3, it is like 8, and it shoots up very fast. And it becomes something like this. You can verify that this is how it acts. As I go to the negative infinity, it becomes something like half to the x, right? Half to the minus x, actually. And that minus x is big, and then you'll go closer and closer to 0. Once again, this will never be 0. And all of these things are, you'll somewhat get similar things. Now, what happens when, just for curiosity, this is not really interesting. So what happens when a is equal to 1?
There it would be a straight line. All
It will be a horizontal line,
yes.
right? So the y-intercept is still 0, 1, but it's a constant function. So what happens as you change a? You can probably do this also in Desmos or something. You can keep a as a parameter and keep changing it. You'll see that as you approach 1, the nature of the graph, so when you're close to 0, it probably flattens out like this as you approach 1, and then it starts going like this. Beyond 1, it starts becoming, the larger the value, the steeper the graph. I cannot draw this well over here. I suggest you use a graphing software and see what happens as you approach 1, and then what happens at a is equal to 1, and then how it flips as you increase the value of a. All right. So this is the nature of the graph of the exponential function. Now this is another thing which is just given as a fact. So hopefully you guys have already encountered this number e. It's an important constant, an irrational number. One way to compute it is as the limit of the sequence 1 plus 1 by n to the n, which is connected to interest rates or the applications there. You can see. You can look at the prof's video also. He has explained how it is linked to some
Yes.
real life phenomenon. But even otherwise, even without interest rates, it's a very important constant in mathematics. It arises in many places. It doesn't have as simple a description as phi, where you can define it as the ratio of circumference to diameter or something like that. That, as far as I know, such a natural, simple definition of that is not there. It is all in terms of sequences and stuff like that. But it is an important constant. It's an irrational number. All you need to know is it's an irrational number. It's a constant, and for curiosity, you can keep this also in mind that it is some irrational number between 2.7 and 2.72. All right, so e to the x is a very important guy. In particular, so we have studied exponential functions over here. In particular, if you want, if you set a is equal to e, this is what you call the natural exponential function. And more properties of it, like all these properties are still there because a is greater than 1, you'll have all these properties for free. And then there are some other properties also, area under the graph and all that the prof has discussed. I'm not going to take that up. You can refer to that video. All you need to know is it's an irrational number, and it's called Euler's number. It is denoted by E. Okay. Hopefully in the future, the importance of it you will see.
It's the base of natural logarithms also.
Yeah, well, that comes. Well, this is called the natural exponential, so that's the inverse of that. So that's the natural logarithm. Uh, there is no way to explain one without the other. No? So there also I have to say that it is the base is just E. So that's it about the exponential functions. Now we'll go to composition of two functions. So composition of two functions is some sort of a natural operation on functions wherein so what do you understand by functions? It's like you have a set of elements and then you map them to another set of elements. And now, so this is something like the input. And if you operate the function, you will get the output. And now if you want the output, and then if you want to further act another function on it, then this becomes the input space for that second function, and then there will be an output, right? So you're doing two steps of functions. So that is what is called a composite function. If you want some example, it'll be like, let's say, taxing something where there is discount, right? So I have some flat something some amount of suppose the price of an item is X, and then I have a flat Y off, but then there is some tax percentage that I have to apply. So this is actually a composite function. So what is the composite function? So let me just write it as f1 of x is x minus 500. Let's say on every item you have 500 rupees off. All right. So what is f1 of x? f1 of x is the discounted price. Right, but on every item you also have, let's say, some tax. So this is price after tax. Now, if I want to calculate the price of an item, how will I do it? First, I will deduct whatever the discount is, and then I will tax it, right? So this is actually what? This is f2 of x minus 500. Is this clear?
Yes, sir.
Yes.
But what is this? This is in turn is f2 of f1 of x. So if you look at this sort of diagram, so we started first with x. and we got to x minus 500. And then there is a scaling factor 1.18 of that thing, of x minus 500. So there were two functions applied on some starting value. So this is what the composition does. So if you have two functions f and g, the composition of f and g is obtained by first taking x, applying g, and then you take that output, which is, so if you just start with x, you do g of x, and then you do f of that. So that is called the composite function. Composite function f of g. Now f of g and g of f may be different. This is somewhat loosely written over here in this block because I've not defined what the domain is and so on. So let's take an example. I think, okay, here there is already an example. Good. So now if I have square root of x and x plus 1, what would be, so first let's take f of g. What is the domain? Range. And whatever properties else you want, you can calculate. Let's just do domain and range. And description, of course, we have to write it down. Now, what element would qualify as an element of the domain of f of g? So if I want to do f of g of some x, first of all, it has to be in the domain of g, right? Because
Yes,
first
G.
you're going to do, yeah. So what are the conditions that I require? X belongs to domain of g, but that's not the only condition that I require. The other condition that I require is that this g of x has to be in the domain of f. Otherwise, you cannot do f of g of x. So ultimately, you want to do f of g of x. Now, what if g of x is not in the domain of f? Then this operation doesn't make sense. So these are the two conditions that are required to have x to be in the domain of. So this, if and only if x is in the domain of f of g. So to check if something is there in the domain of the composite of two functions, then these are the two criteria that need to be verified. Let's do it for this particular example. So what is the domain of G? Assume largest possible domains in this case. So what is the domain of G?
Minus infinity plus 1 to infinity.
What is minus infinity plus 1 to infinity? So you can just have it as the whole space, right? Why is there
Is the real.
Yeah.
or you can say minus infinity to infinity. That's also the same thing. I didn't get that plus 1 part, but that's fine. Now, what happens to the range of G?
One.
What is the range of G? Anyone?
One.
This,
In
this is also R, because you're not just taking positive values, right? You're taking any X. I'm just looking at range of G right now. Even if you look at the graph of it, it will just be something like this. Straight line with one y-intercept and slope equal to 1. So this has range also as R. But what happens when I do f of g of x is that if I want to do f of g of x, what is the domain of f?
Minus 1 to infinity.
Domain of f is what I'm asking for.
All positive integers.
Well, you don't need to restrict yourself to
Real,
integers.
all real.
Natural number.
It can take any value. Domain
Zero
of
to infinity, yeah.
Close 0 to infinity. Now, if I want g of x to be in the domain of f, that is what I have to check, right? So that's what this says over here. But even otherwise, I want the g of x f to be able to act on g of x. So this is the same as saying g of x is in 0 to infinity. But what is g of x? That's nothing but x plus 1 is in 0 to infinity. So when would x plus 1 be in 0 to infinity?
And next will be in -1 to infinity.
So if x is in -1 close to infinity, x plus 1 will be in 0 to infinity, x plus 1 happens to be g of x. So then I can do f of g of x. Right, so let's verify that as well. What is f of g of x? So I take f of g of x, which is f of x plus 1. G of x is x plus 1, so I do f of that, which in turn is square root of x plus 1. And it is easy to verify that the domain of this function is -1 to infinity. So the domain of f of g is -1 to infinity. Okay. And what about the range?
Zero to infinity.
0 to infinity.
Open, closed, you need to say something.
Close 0 to infinity.
Yes. So range of that is close 0 to infinity. Can you tell me what the graph of this looks like? Graph of the composite function? Any guesses? No. So first of all, it's defined only from -1 to infinity. So I'll only be looking at the part of the graph to the right of -1. At -1, what is the value of the function?
Zero.
0.
0. And at 0, what is the value of the function?
1.
1.
So 1. And then, so from -1 to 0, there was a jump of 1. But 1 to 2, there will be a smaller jump. It becomes √3, which is 1.7-ish. So what is the nature of this? Can you guess?
It's an increasing.
It's an increasing function, yes,
It will tend
but it's just a parabola. It's part of the parabola.
Yes, sir.
So if you say y is equal to square root of x, is it not just this one? So y square is equal to x. We saw this y square equal to x, right? That was
Yes.
this sort of parabola, and that's not a function because the positive value of y as well as the negative value of y comes into picture. But if I write y is equal to square root of x, there we are taking only the positive square root. So what I'll end up with is this. Now, if the argument is not x but x plus 1, this graph gets shifted by 1 unit. So what I'll get is the axis will come over here. That's all. So this gets at -1, which is exactly what we have drawn there. So such things you can train yourself on how to figure out what the graphs are, because most of these functions are known, right? It's polynomial functions. Now, if it's some ratio of two linear functions, all that is not that easy to plot. But these things you can try. It can be a good exercise just for your curiosity, at least, to try and plot the graphs of the functions that you encounter. What about GOF? I don't know if there's enough space to solve the whole thing. So I'll just write this over here. What do you think the domain of G of F will be? You can take a bit of time if you want and figure out what the domain of G of F is. There are two conditions that need to be checked. One is that X is in the domain of F, and then F of X is in the domain of G.
Combined equation will be root x plus 1, right?
Yes, the composite function description is root x plus 1. Well, if you do it that way, then
infinity, sir.
yeah, that's correct, 0 to infinity, because the domain of F itself is 0 to infinity. And it doesn't matter what you take in the domain of F, the square root of that will be some real number. Since G has the domain as R, there is no real condition on F of X having to be there is vacuously satisfied. All right, if you did not understand this, take this as an exercise. It's easy enough to figure out. And what about this? What is the range of G of F?
Close 1 to infinity.
Is that correct? Yeah, that's okay. GOF of X is root X plus 1. So here the minimum value of square root of X will be 0. So the minimum value of the function itself will be 1, and it can go up to infinity. And if you want the graph of it, can anyone quickly guess? So when you have the graph of some function and then you add a constant on the outside, the graph gets shifted vertically. So this will be this. Everything has an increase in height by 1. So you know the graph of root x, you know the graph of root x plus 1. You just push the height up by 1. Okay, so that's about composite functions. This was a slightly simpler example. You can take a look at the assignment, extra practice assignment questions, and maybe even in the doubt session, you can, if you have examples which you could not figure out, you can bring it up there. But the idea is the same. These are the two conditions that need to be verified. That the domain of the composite function contains elements of the domain of the first function. By the first function, I mean the function which acts first, not which appears first when you read. So the The domain is a subset of the domain of the first function with the condition that the image under the first function should land in the domain of the second function. If that's a bit much, you just remember these two conditions. And you don't really need to remember it. It's very natural to see when you understand what the composite of two functions does. Is that clear?
Yes, sir.
Okay. So that's that. And the last thing is the inverse of a function. Yeah, here we'll take examples also. Right. We have discussed this earlier. That is the remark that comes in the beginning. So given a function, if you look at elements of B, it could have multiple pre-images. But if the function is 1, 1, then each element in the range, not element in B. In B still you could have elements without pre-images. So same mental picture you should have is something like this, where if it is 1, 1, you will not have multiple elements of the domain mapping to the single element, but there could be some guys left out. That we don't care about. We just let them be. We define the inverse from the range itself. So without the assumption that the function is 1, 1, you cannot guarantee whether the inverse exists. As we had seen in one of those visual examples, we had something like this. And in this case, you cannot really define the inverse, because what will you assign as the image of this element? You should do one of the two, but that is not a well-defined description. So if there is some choice, then that is not a way to define anything. So such a choice you can avoid by demanding that it is 1, 1. But in general, we'll just say that an inverse is the function which satisfies these two conditions. Now, this is defined in terms of the composite. This is F inverse of F, and this is F of F inverse. So this is what I meant earlier when I said that this in some way does the undo on what F does, the inverse function. So if I have A and then B and then consider A again. So if I have some element going to this element, so A goes to F of A. Then what did I say? What was the property of the inverse? It maps every element to its pre-image. So this will go back to A, right? I can write a function G. But what happens in this case? G of F of A is equal to A. So this G is what we call the F inverse. So if F takes A to F of A, then F inverse will take F of A to A. So it is just that it maps to its pre-image, and that pre-image is unique if we assume that the function is 1, 1. Is the definition clear of what the inverse is?
Sir, how do you
It will
calculate?
be, yeah, that we'll see. Now, give me, let's take any linear function. So linear functions are 1, 1. Now let's say y is equal to ax plus b, or let's take some 3x plus 2. What is the geometric description of this? This would be a function with y-intercept equal to 2 and slope is 3. It is not 45 degrees, but it is some steeper angle. So roughly something like this. Okay. So let's say this is y is equal to 3x plus 2. Is this a 1-1 function? We have already seen that almost all lines are 1-1 functions, except, the horizontal lines, and vertical lines are not even functions. So all other lines are 1-1 functions. Now, if I want to calculate the inverse of it, so the function is f of x is equal to 3x plus 2. Now I want to see what f inverse of x is equal to, right? Now suppose f inverse of x is equal to y. I want to determine what y is, right? What is the property of the inverse function? Now if I act f on both sides, I'll get f of f inverse of x is equal to f of y. Is this clear? Is this step clear?
Yes, sir. Yes,
Okay.
sir.
Now what is f of f inverse of x? So once again, you keep this in mind, right? So when I say f inverse of x is equal to y, this thing is some y, and this thing is x. Now, if I go to f inverse, and then f will take me back to x, right? X is an element of the codomain. Here it is r and r, but I'm just writing it as a and b in general. So f of f inverse of x, and by definition also that is what is said over here. For all x in the range, you have f of f inverse of x is equal to x. So this side is easy to simplify. So this is x. But what about the other side?
Three y plus 2.
By definition, f of x is 3x plus 2. So this would be 3y plus 2 because we're looking at f of y. Now, can I rearrange to get the value of y in terms of x?
Yes, sir.
X minus 2 by 3.
But y was just f inverse of x. All right, so you can get the value of, for simple functions, you can calculate it this way, but there might be functions for which you will not get it so easy. But this is the procedure. And for the problems that you will be getting, this will
I'm
work.
fine with this one, like x minus 2 by 3, because that is how
Yeah.
it. But I'm not getting this x is equal to 3y plus 2. How you are writing this?
So this became this and this became this. So which one or two? Which one are you not?
Uh, uh, 2 second, because if we look at the function y is equal to 3x plus 2, so we have to
Yeah.
take to that
No, not
side,
y
to the
is.
left hand side. So it becomes y
Okay.
minus.
Let's just you can keep anything else. So uh, in fact, okay. If we have said that y are the elements of the codomain is what we have been using. So let's do this. This is better, right?
Yeah.
So this would be this, and this would be this. So you can say that. Wait, what have I done? Oh yeah, that's okay. Yeah,
X equal to.
f inverse of y is equal to y minus 2 by 3. Is this
Yeah.
less confusing? Yeah. Yeah, yeah. Eventually X and Y. Yeah, but it is good to have one convention for domain and one convention for code. So let's keep it that way. So F inverse of an element in the codomain, we can write it in terms of the codomain, and we can verify if you want that this actually satisfies f of f inverse of y is equal to y and f inverse of f of x is equal to x. Now, yeah, even over here you can, if you want, you can make this as y because elements of the range are denoted by the letter y. Yeah, this is y. Yep. So yeah, let's verify this. If I do f of f inverse of y, what is f inverse of y? F of, so here you see, yeah, you'll see why I said that we are okay with using just this as the input also. So just by definition, f of f inverse of y would become f of, as per our calculation, y minus 2 by 3. But what is f of y minus 2 by 3? By definition, it is 3 times y minus 2 by 3 plus 2. And what do you get if you simplify this? It's not that hard. What's the answer?
Sir, it's just y.
It's just y. And the other verification also, if you start out with f inverse of f of x, you'll get f inverse of f of x is 3x plus 2. And then f inverse by the formula, it is the argument minus 2 divided by 3. So this takes the role of y. Right? So 3x plus 2 minus 2. So this is just 3 something plus 2, which is the definition of f. 3x plus 2. F of x is 3x plus 2. So f of y minus 2 by 3 is 3 times y minus 2 by 3 plus 2. So similarly, we do the same thing for this, and what you get is x. So f inverse of y is y minus 2 by 3. This is the conclusion. Now, one more common theme of problems, let's say, is something of the form x minus 1 by x plus 1. Now, what is the domain of f?
R minus 1.
R minus minus 1. What is the range of f?
That is R.
You will probably not get all of R. What value will you not get? So if you say this is always equal to C, then writing x in terms of C, you'll see x minus 1 is Cx plus C. C plus 1 divided by 1 minus C. Actually, yeah, you'll not get 1. So this will never be equal to 1. Can this be equal to 1?
No, sir, it will never.
Yeah. Yeah. So to see that, you can actually try to compute the inverse of this. So if you look at, suppose f inverse of some element y is equal to x, then you do the same trick, apply f on both sides. What you'll get is y is equal to f of x, and then that will be x minus 1 divided by x plus 1. Now if you rearrange, you'll get xy plus y is equal to x minus 1. Now I want to write x in terms of y. So I'll group up the x terms on one side. I'll get 1 plus y is equal to x times 1 minus y, right? Then I'll get x is equal to 1 plus y divided by 1 minus y. And x was f inverse of y. So the inverse has this description. But this is not, this is, what is the domain of the inverse?
R minus 1.
But you remember what is the domain of the inverse? It is actually range of f. So even if you don't know this, suppose you don't know this statement is always true. If you have a one-to-one function, then domain of f inverse is range of f. You see over here, by definition, we remove the elements of the codomain which do not have pre-images, and what we are left with is the range. So we are defining the function f inverse on the range, meaning it is its domain is the range of the original function. So here you can see that the domain of f inverse is actually r minus 1. So both of these are equal to r minus 1. Is that okay?
Yes,
Yes,
sir.
sir.
Yes.
So here also you can argue that this also shows that this function is one-to-one. Is the fact that this function is one-to-one very obvious? It's actually not. But then the inverse of some element is not turning out to be uh, two possible answers or anything. To explain that point further, let me give another example. Let's take now obviously not one function. Let's take f of x is equal to x square. Now if I use the same algorithm to try to compute the inverse of we should run into problems, right? This should not work because the inverse of this does not exist, because there are elements in the codomain or in the range that have multiple pre-images. In fact, almost all of them do have multiple pre-images. So suppose I write f inverse of y is equal to x, or y is equal to f of x, then y is equal to x square. Now what I want to do is write x in terms of y. But to do that, I have to take this square root. But you see what problem arises? F inverse y is not uniquely determined. It has two possible values. So f inverse cannot be a function. Is it clear?
Yes.
Yes, sir.
Yes.
Yes, sir.
All right, so that is all. For today's session. There's no other topic remaining, I believe. Right. Okay. There's one more remark, and that's another way to look at the inverse of the function. Now, graph of the inverse. Let me just write it down. Now, what is so? Suppose f is a function. Let's say it's 1, 1. Let's say its inverse exists. All those whatever nice conditions that need to be satisfied will be satisfied, and the inverse exists. This is our assumption. What is the point on graph of f look like? I'll just write graph of f. Usually we do not we write gamma of f. What does it look like? What do the coordinates look like? Maybe the question is vague, but are you convinced that they are of the form a comma f of a for some a? But an arbitrary point on the graph of a has this form. Now f inverse is a map from, let's say, range of f to a. What is the point on graph of f inverse look like?
F of a comma a.
Yeah, let's start with b, f inverse b. This is by definition, right? By definition, it should be of the form input, comma, function of the input. The function that we are considering here is f inverse. So a typical point would look like b, comma, f inverse of b. But where is b? B is in range of f. This would imply that b is equal to f of a for some a. So it is the image of something. That is what it means to say that b is in the range. Now, if I substitute b is equal to f of, let's just say a naught to distinguish it from the earlier one. So if I substitute b with f of a naught, what I get is f inverse of f of a naught. That's enough brackets, I think. Yeah. So what is the second term? What is the second coordinate? By definition,
A naught.
a naught.
Yes.
Right. So if a comma f of a is a point on the graph, then f of a comma a is a point on
Inverse
the graph of the inverse function. Now, do you know what the relationship between these points x comma y and y comma x are? So what happens if I
Symmetric.
flip the coordinates? Symmetric about what?
straight lines at y equal to x.
So let's take specific examples. Let's say I take the point 1 comma 3. 1, 2, 3, 1, 3, something like this. So where would 1 comma 3 be? It would be over here, right? This is 1 comma 3. Where is 3 comma 1? It's over here. So a property of reversing the order of the coordinates, this is something that you can verify. This what I have given here is not an explanation of why that happens, but it is just a demonstration using a particular example. So if you flip the coordinates from xy to yx, what you get is actually the mirror image of the point across the line y is equal to x. So what happens, let's say if I take something like minus 4 comma 0,
0 comma minus
what is
4.
the, yeah, 0 comma minus 4, which happens to be the mirror image, right? So if I take something like 1 comma minus 1, now you can do whatever you want. Minus 1 comma 1, its mirror image is this. So the mirror is just y is equal to x. What y is equal to x acts as the mirror. Or yeah, it's called the reflection about the line. So back to the graph, if I have the graph of a function, you have to take its reflection along this line. So let's take the earlier example itself. Y is equal to 3x plus 2 was our original function, right? F of x. What was f inverse of x? I'll use x now because we are using it as an input variable. This was x minus 2 by 3.
By 3.
Now let's try to draw the graphs of these things. It should be mirror images. Let's just verify that to whatever degree we can. So this is something like this. If I have, assuming that this is slope 3, what about the other guy? It has a y-intercept of minus 2 by 3, which is somewhere over here, and it will be something like this. And the slope is 1 by 3. It'll be something like this, and there will be this line y is equal to x will act as a mirror for the two. So upshot is that graph of f inverse is the reflection of the graph of f. So when you say reflection, you have to specify across what mirror. So across the line y is equal to x. Okay, so now you can take one-to-one functions, take square root of x. Instead of computing its inverse, well, you can look at it and you can see what its inverse is. It might be a fun exercise to just plot it by hand. You know what the square root of x looks like. Then try to compute its reflection just visually, and then try to guess what what the inverse of the function. So to understand this procedure even better, you can take this as an exercise. Right. So that's all there is to discuss in week 5. Now, yeah, if there are doubts, I'll take it now.
I have doubts in graded assignment.
Graded assignment for week 5.
Yes.
A graded assignment doubts cannot be discussed before the deadline is done. So you'll have to try to figure it out yourself.
Sir, can I test technical question?
Yes.
In the final exam, what will be the weightage of each week?
That will be notified to you before the exam. I'm not sure if it has been decided yet, but you will be given enough notice about the rough split up. Yeah. Usually you will have more weightage for the week 9 to 12 content, 9 to 11 content, because quiz 1 and quiz 2 will have already covered stuff until week 8. So weightage will be more, that is for sure. The exact percentages will be revealed if yeah, the policy, whatever the policy is for this term, it will be you'll be there will be a discourse post.
Grading policy.
Sorry. The grading policy doesn't have the split up of weekly content for the end term exam. Usually it is term specific and course specific also, but you will get to know. Either a portal notification will be sent, common email, or a discourse post, or both. Well ahead of time will be communicated. All right, if there are no other doubts, we can wrap up.
So can I explain the one more example, sir? Graph of inverse function.
Graph of inverse function. Okay.
Yes, sir.
And this page doesn't have. Let's try to plot the graph of f inverse of x, sine inverse of x. Now, if I consider the function sine, you can consider it as a function from R to R, but you know what its range is. What is its range?
1 to -1. Yes.
Yeah, -1 to 1. But yeah. So, but what is the problem with this function? If I'm trying to compute the inverse, what is the problem?
It's a wave.
It's a wave is okay. That's not a problem. For the purpose of computing or understanding the inverse, what is the obstacle?
Horizontal line test.
Yeah, so it's a many to one function. That's the problem, right? Now, if you look at the graph of sine, but this might not be very easy to do by hand. Just give me a moment. This is okay. It'll be something like this, right?
Yes.
So if I want to compute the inverse, the first thing that I said was we need to consider a one-to-one function. This is clearly very not one-to-one. But if I want to look at it as a one-to-one function, what do I need to do?
Horizontal line test.
I would want to only focus on a part where it is one-to-one. So what would that sort of part be like? Restrict the domain.
-1 to 1.
The domain should not be -1 to 1. It is something else. It is minus
half to half.
Negative.
on what domain is sine injective? What is the maximal domain on which it is injective?
Sir, we can say that it is minus pi by 2 to pi by 2. We can say it is
Yes.
injective.
Even -1 to 1 will also work, but that will not give you the whole range of on the other side. So if I restrict from minus pi by 2 to pi by 2, what I'm doing is I'm just focusing on this section of the graph where it starts at -1 and goes to +1, something like this. Okay, now how does the line y is equal to x behave? Does it go above or below? Do you know?
Yes,
So
sir.
how does it go? So this line
Below
y is
that
equal to
curve,
x, is it like this or is it like this?
like the first
So
one.
this might actually be a more complicated example, because if this is the line y is equal to x, right? So something like this. Hopefully it passes through the origin. No. Okay, that's good enough. Your sign will actually be like this, because the slope of this is always 1 and this is cos x, and that will be lesser than 1. Only at that it will be 1. So okay, maybe not sine. Okay, this is also sort of harder exercise. You'll need to know the slope of it. You can do this. You can do take the line y is equal to x, and using Desmos you do this. Just to understand the concept, you can still do this. If you look at, so here is what you will do to understand what is happening. So first you do y is equal to x, then you do y is equal to sine x, and then you do y is equal to sine inverse x. Then you see how the graphs of sine x and sine inverse x are with respect to this line. They will be reflections of each other. Okay, so you'll have something like this. So on the one hand, you will have the sine wave, and on the other, you'll have the sine inverse wave, which is something like this. It should be like this, no? Yeah. It'll be something like this. You'll see that they are reflections of each other. So this is a verification that you can do.
Sir, sine
Okay,
inverse
so
wave will run along the y-axis, or it will be on x-axis only?
it'll be on the x-axis, like the input is x, the sine inverse x is the y coordinate. So we are looking at the inverse function as with the inputs in x itself. We are writing it in terms of x.
Okay.
Okay. So to understand this, that is okay. Or okay, let's do this. What is the slope of the reflection of a line? Reflection along y is equal to x again with slope m. This is a good exercise. So first let me explain. what the questions. This is once again kind of far beyond what is required, but it's nice. So suppose I have this line y is equal to mx, some m, and I have this line y is equal to x. If I take the reflection of the line y is equal to mx, what will I get? I'll get some line, right? And it also has to pass through the origin. So this line in the new color is the reflection of the line y is equal to mx, and this is equal to y is equal to some m prime x, because this is also a line through the origin, so it's of the form y is equal to m prime x. What is the relationship between m and m prime? Can you determine?
One upon m.
It should be 1 upon m, but why is it so?
I don't know. It
So
just seems instinctually right.
good, that's good intuition. So m prime is equal to 1 upon m. Let us see why. So if this angle is theta, if this angle is theta, then what is this angle? What is theta prime equal to?
Ninety minus theta or something like that.
Yes, it is 90 minus theta. So you're again using your intuition.
Yeah.
You can verify it with some, because it's the reflection, you will have that angle of reflection is equal to angle of whatever, and then you can verify that this is equal to pi by 2. All right. So what happens to tan of this? Tan theta prime is equal to tan of pi by 2 minus theta. But what is tan of pi by 2 minus theta? It's cot theta, right?
Yeah.
Yes.
And that is actually 1 by tan theta. But what was tan theta? By definition, tan theta is the slope of the line, and tan theta prime is the slope of the new line. So m prime is equal to 1 by m. So the reflection has the slope 1 by m. But now we'll prove the same thing. So this is like proof 1. And proof 2, we'll use this fact that the reflection of y is equal to mx is the inverse of that function. So if I have the function f of x is equal to mx, what is its inverse? So suppose f inverse of y is equal to x, as we have been doing, then we'll have y is equal to mx and x is equal to 1 by my, or f inverse of y is equal to 1 by my. Now I'll just change the variable to f inverse of x is equal to 1 by mx just because of that. And what is this? This is the standard line, a standard expression of a line which passes through the origin with slope 1 by m. If I know the fact that the function and its inverse are reflections of each other, this also you can use to conclude that m prime is equal to 1 by m. Okay, so this is another example or demonstration or whatever it is that you would want to see why. So even if you did not know that the reflection of the inverse reflection of the graph of a function gives the graph of the inverse of the function. Even if you did not know that, you can just do trigonometry and at least for the straight line case and check that the line that you get by reflecting the given line actually happens to be the inverse line. Is that fine?
Yeah.
Okay, I think, yeah, now it's 20 minutes past and we'll stop here. And maybe take up the quiz doubts also in the next one. I think I'll stop here.
Good night, sir.
Thank you, sir.
All right. See you guys whenever next. Bye.
Thank you, sir.